Why is measuring thermal conductivity at extremes so hard? Imagine trying to measure how well a material conducts heat when it is being pushed to its limits. It's like trying to weigh a fish while it's thrashing in your hands. That's what makes measuring thermal conductivity at extreme conditions so tricky. Thermal conductivity tells us how easily heat moves through a material. Under normal conditions, it's pretty straightforward to measure. You apply a known amount of heat and see how the temperature changes. But when temperatures soar or plummet, things get complicated fast. First, materials don't stay the same at high or low temperatures. They can change their phase from solid to liquid or gas, or even undergo chemical reactions. These changes make it hard to get consistent readings because the material's properties are constantly shifting. For example, a metal might become brittle or melt at very high temperatures, or become very fragile when cooled to extremely low temperatures. This unpredictability makes it tough to pin down a single value for thermal conductivity. Sensors and measurement tools also face big hurdles. High temperatures can damage sensors or cause them to give false readings. Radiation from nuclear environments or space can interfere with electronic sensors, messing up the data. At very low temperatures, sensors might not work properly because they can become sluggish or stop functioning altogether. The environment itself can be hostile, with corrosive gases, high radiation, or mechanical stresses that can break or degrade the equipment during testing. Controlling heat flow at these extremes is another challenge. At high temperatures, heat can escape rapidly through radiation, which is hard to measure accurately. Isolating the heat flow from other forms of energy transfer becomes a real puzzle. When temperatures are very low, heat transfer slows down, and small fluctuations can have big effects on measurements. This makes it difficult to get a steady, reliable reading. Sample size and shape also matter. Some tests need tiny samples to fit into specialized equipment, but handling such small pieces at extreme conditions is tricky. Small samples can make it harder to measure heat flow accurately because the surface effects become more significant. Different measurement methods have their own problems too. Steady-state methods take a long time and can suffer from heat losses, while transient methods are faster but requiring complex calculations that are harder to do when conditions are unstable. Finally, the properties of materials can change rapidly during measurement at extremes. Temperature swings or phase changes can happen in seconds, making it hard to get a clear picture of what's happening. All these factors combine to make measuring thermal conductivity at extreme conditions a real challenge. It's why scientists need specialized equipment, careful planning, and sometimes creative solutions to get accurate data. This data is vital for designing safe nuclear reactors, spacecraft, deep earth drilling tools, and advanced materials. Without it, working in such harsh environments would be a lot more dangerous and less efficient.